High-level programming languages like C and C++ offer an intuitive, abstract logic for developers. But beneath that abstraction, every single compiled instruction maps directly to the rigid, inescapable constraints of physical silicon. This is the Intel 386DX. It was the first processor to implement the IA32 instruction set, expanding the 16-bit registers of the 8086 into a 32-bit architecture. In highly orthogonal reduced instruction set computer, or RISC architectures, developers can utilize virtually any register interchangeably for operations. The IA32 architecture fiercely retains the complex instruction set computer, or CISC philosophy. CISC is a processor design where single instructions can execute multi-step operations directly in the hardware. In this environment, silicon-level roles are strictly hardwared. The architecture designates highly specific structural and algorithmic tasks to individual registers. We will explore three core mechanics of this design: the rigid taxonomy of the registers, the inverted topography of the stack, and the state machine driving execution. Whether optimizing compilers for performance or analyzing evasive malicious payloads, mastering modern software requires submitting to the historical and physical limitations of this specific hardware design. Look at the schematic of the foundational 32-bit register file. The design specifically isolates the general-purpose data accumulators, like EAX and EBX, from the rest of the processor. These accumulators are modular. They can be cleanly fragmented to access highly granular, byte-level data without disturbing the upper bits of the register. Contrast this flexibility with the architectural solid registers, the source index, or ESI, and the destination index, or EDI. An attempt to move a discrete byte into the lower 8 bits of the source index will categorically fail at the compilation phase. These solid registers physically lack native 8-bit subdivisions in the IA32 specification. This indivisibility is a direct artifact of the architecture maintaining backwards compatibility with the original 16-bit 8086 processor. In that legacy 8086 design, index registers were engineered purely as 16-bit memory pointers. Intel preserved that structural boundary when they expanded the architecture into the 32-bit extended registers. The hardware instruction decoding matrix lacks opcodes to address a byte of ESI. Compiler instruction selection remains bottlenecked by hardware decisions finalized in the 1970s. The IA32 hardware provides accelerated string operations, such as move SB for single bytes and move SD for double words. These specialized instructions shift the burden of address incrementation entirely out of software loops and directly into the CPU's microcode. To initialize the operation, the software loads ESI as the authoritative pointer to the data origin, and EDI designates the target memory location. When a repeating prefix is invoked in the code, the CPU microcode takes over. It autonomously fetches the byte, writes it, and increments both pointers without requiring any explicit arithmetic instructions from the developer. Moving contiguous data creates a mathematical hazard when dealing with overlapping memory spaces. A standard forward-moving copy operation will predictably overwrite data at the beginning of the destination before that exact data can be read as the source, resulting in a corrupted cascade of overwritten bytes. Developers avoid this by setting the direction flag using the STD instruction. This single hardware bit forces the CPU to automatically decrement pointers after every transfer, processing the memory matrix safely in reverse. Under default hardware rules, memory addresses held in the ESI register are implicitly hardwired to the data segment register. Here is the CPU address generation logic. In niche scenarios like custom OS development, reference data might reside outside its mapped segment. Developers use a segment overwrite syntax, like an ES prefix, forcing the hardware to fetch from the extra segment descriptor instead. Raw memory pointers only supply a starting coordinate. They lack an inherent bounding box. Moving raw numbers directly into memory requires strict assembler directives, such as DWRPTR, to dictate exactly how many sequential bytes the execution unit must write. IA32 memory management relies on explicit directional flags, segment overrides, and byte-size directives to command the physical hardware and prevent systemic data corruption. The procedural integrity of high-level languages relies on the execution stack. This dynamic memory block safely stores function parameters, local variables, and return execution addresses. This diagram outlines the stack's spatial topography. The stack pointer, or ESP, is anchored at a high memory address, in this case 0x1000. It inherently grows downward toward lower memory addresses to maximize allocation space and avoid collisions with the dynamic heap. Because the stack grows downward, pushing a 32-bit register onto the stack causes the hardware to autonomously subtract 4 bytes from the stack pointer before writing the contents to RAM. As temporary data is pushed and popped during complex algorithmic branches, the stack pointer continuously fluctuates. This volatility makes it unreliable for locating data. The function requires a stable referential anchor. Compilers achieve this stability by deploying the standard function prolog. By moving the current ESP into EBP, the base pointer locks into place, creating a fixed referential anchor for the newly created stack frame. With the frame firmly anchored, compilers allocate and access local variables using negative spatial offsets, traversing logically downward into the lower memory addresses of the newly created space. Modern microarchitectures mandate that data accesses perfectly align with the physical boundaries of the CPU's L1 cache lines. Attempting to read an unaligned integer forces the processor to execute 2 separate memory fetches, triggering severe hardware penalties across the memory bus. To forcefully comply with interface standards, applications execute a bitwise mand operation against the stack pointer. By logically masking the address against the value -4, the lowest bits are stripped to 0, mathematically guaranteeing a clean 4-byte stack alignment. A compiled function's memory layout is an inverted, precisely anchored physical topography designed to maximize RAM allocation while mathematically preventing architectural bus faults. Moving from memory topography to execution flow, the fundamental rhythm of the CPU is governed by the instruction pointer, or EIP, which tracks the precise linear offset of the fetch, decode, execute cycle. EIP is highly insulated by the architecture. A developer cannot modify it directly with a standard assignment instruction. Altering the execution flow requires specialized control flow instructions that inherently instruct the processor to securely evaluate target privileges. The translation of raw machine code into those conditional execution traces is governed by the E-flags register, seen here as a 32-bit hardware control board. During execution, the arithmetic logic unit evaluates mathematical outcomes. If an operation yields a negative result, the hardware automatically mirrors the most significant bit directly into the sign flag, dynamically redirecting the instruction pointer. This granular state tracking allows debuggers to manipulate the trap flag at bit 8. Raising this flag forces an internal hardware interrupt immediately after an instruction completes, pausing the execution pipeline for granular single-stepping. Advanced malware actively abuses this trap flag to force virtual machine exits. The malicious payload observes if a hypervisor perfectly mimics the hardware timing of the interrupt delivery, allowing the malware to detect and evade sandboxes. Conclude that dynamic logic is entirely subordinate to these physical flags, where basic Boolean math and timing interrupts define security boundaries between analysis and exploitation. Mastering IA32 constraints allows compiler backends to deploy micro-optimizations that exploit the physical and electrical characteristics of the processor's execution pipeline. A ubiquitous requirement in logic processing is clearing an accumulator to 0. The intuitive high-level approach is an explicit move instruction, such as MOV EAX 0. As this comparison shows, modern compilers universally reject that instruction. They prefer a bitwise exclusive OR operation against the register itself, XOR EAX EAX. This method frequently resolves entirely in the decode stage, bypassing the execution unit. Any Boolean value exclusively ORed with itself mathematically evaluates to 0. This sequence requires fewer instruction bytes, breaks internal register dependencies, and frees up execution clock cycles. The singular exception where a compiler must use the spatial and execution penalties of a move instruction is when the algorithmic logic strictly requires the preservation of the current E-flag state, because logical arithmetic inherently modifies those flags. Developing, optimizing, and securing software for the IA32 ecosystem requires an exact understanding of its foundational silicon topography.